So, welcome to this second class of this microscopy, and here in the last class we have just dealt with some basics related to the lens system and also the how the electrons are produced by using the filaments, and these are accelerated by Lorentz force which is provided by using the electromagnetic lenses. Now, these electrons are actually, for example, they are interacting with the specimen, and depending upon the thickness of the specimen, different types of signals also can be produced and can be used for the several imaging purpose or the spectroscopy purpose. So, in this diagram what I am showing is the interaction of an electron beam with a sample which is thin enough, so that so these electrons will interact with the sample to produce the secondary electrons. They can produce the backscattered electrons. These secondary electrons and the backscattered electrons can be used in SEM for imaging purpose. Okay. Then they also release the Auger electrons that will come back, will come to that in subsequent discussion, and also they also produce X-rays which are very important for the elemental compositional analysis. So, these are energy dispersive spectroscopy, and these X-rays have a characteristic wavelength corresponding to the element present in the sample. So, you can get the quantification of the or the composition of that particular sample. If the sample is thin enough, then there will be a transmission of this electron beam across the sample, okay. And if you provide a screen here, all the fluorescent screen, what we can do, what we can get is the these transmitted electrons can be collected, and out of this transmitted there will be certain electrons which are elastically scattered, and there will be certain electrons which is inelastically scattered. Based on the elastically scattered electrons or the inelastically scattered electrons, you have a different types of functions. Okay. So, elastic scattering, it means that there is no energy loss. Inelastic scattering, where there is an energy loss. Okay. So, means while interaction of the electron beam with the sample, there will be a certain energy loss, and that loss in energy can be converted to certain other secondary radiations. Okay. And we will discuss about these radiations in details in the subsequent slides. Now, first thing is to understand is some basic terms related to the interaction. The two basic terms which usually deal with is the cross section and also the mean free path. Okay. So, when the primary electrons enters the specimen, same or different electrons leave again to form image. Okay. Different electron means these primary electrons will knock out the electrons from the sample surface, and those different electrons can be used for the imaging purpose. So, usually these are used for the secondary electron imaging. These interaction of primary electrons with the atoms in the specimen. Okay. So, with the interaction of these electrons, you will produce images, you will produce the diffraction patterns, and also you will produce the other radiations which are used for the analytical spectrums, for example compositional analysis, correct. So, there are important terminologies which is called a cross section. What is cross section? This is the area which is scattering the particle in the sample appears to present for the electrons. Okay. It means that this cross section or this area is present or for the electrons to be scattered. Okay. So, this is the cross section. Okay. If you consider there is a n particles per unit volume of the sample with the cross section sigma, for a particular scattering event, the probability of a single electron being scattered in its passage through a thickness of dx remember we are talking about area, so there is a thickness dx, then that can be given as n sigma dx. Okay. N is the number of particles per unit volume of the sample, sigma is the cross sectional area, and delta x is the thickness across which the beam has travelled. Okay. Alternative way, we can actually calculate the mean pre-path for the scattering as the inverse of n into sigma, which is called lambda. Okay. So, they have a inverse relationship. So, what is the lambda? From the formula what we can is, this is the average distance which an electron will travel before being scattered. Okay. So, these are the two terms we usually use for the scattering events. So, little bit more about mean free path. It is different for both TEM and SEM specimens. In TEM specimens, for many scattering process, the mean free path is similar to the thickness of the specimen, because TEM samples are electron transparent and the thickness is around it ranges from 20 nanometers to 80 nanometers. Okay. So, these are very thin samples. So, usually the mean free path is similar to the thickness of the specimen. But in SEM samples, where these are bulk samples, okay, which have a few hundreds of microns of thickness, that might be occurring that the electron can be single scattered, plural scattering, or multiple scattering. Okay. So, what is single scattering? It scatters only one time during the interaction of the sample. There are several scattering, or there are many scattering, multiple scattering events in the sample. So, the probability of an incident electron suffering n scattering events while travelling a distance x across the sample, it can be given by a Poisson's equation where Pn is equals to 1 by n factorial x by lambda raised to the power n exponential x by lambda. X, remember, it is the thickness through which the electron has travelled. Now, similarly, if you have a two scattering events, I told about the plural scattering, then this can be given by n can be replaced by 2. Okay. But we can use these Poisson's equations little bit estimate way accurately for some scattering events. But if there are many scattering events, usually the Poisson's equation is not useful due to scattering by different mechanisms. For that, use Monte Carlo methods are used. Okay. So, this is just to introduce the definition of mean pre-path and how it is different in the TEM sample and the SEM samples, and based on the thickness, these probability of incident electrons to be scattered, the n scattering events can be calculated. Now, little bit details will go to the scattering. As I told you, when an electron interacts with the specimen, it either elastically scattered or it will be inelastically scattered. Okay. First, we will talk about the elastic scattering. Elastic scattering, it means that there is no change in the energy of the incoming electron after scattering event. Direction might change. For example, this is a typical this atom. There is a nucleus and there is an electron crowd around the nucleus. If an incident electron comes and scatters, it can be scattered at the nucleus, it can be there is no change in energy, but there is a change in the direction. Some of the incident electrons, they may scatter through the electron cloud, okay, and then they may not with an angle theta, with a larger angle, and some of the electrons they can scatter with a very small angles. So, these are called scattered electrons. If there is no change in energy, then these are called elastically scattered electrons. Okay. So, elastic scattering usually occurs by Coulombic interactions, means electrostatic charges. So, you know that the electron is negatively charged, nucleus is positively charged. So, based on this, you will have a Coulombic interaction. So, between the primary electron and both the nucleus and all the electrons around it. Okay. So, these scattering events is between the electron, both the nucleus and the electron around it. So this particular scattering is called Rutherford scattering. So it is nothing but the strong forward peaked distribution of electrons, okay. And here if there is a E0 which is the energy of a primary electron, then the probability of its being scattered through an angle theta is given by this particular equation, where the probability at an angle theta is proportional to the inverse of E0 square and sin raised to the power 4 theta. It means that higher is the energy of the primary electron, lower will be the probability of the scattering, because it moves very fast, it is accelerated towards the sample very fast. Okay. So, probability of scattering, as there is a term called sin theta here. So, for small angle the probability of scattering is much higher as compared to the large angle scattering. So, if theta is more, then your probability reduces, but for any angle it decreases with the increasing of the electron energy, fine. So, this is the probability of scattering. Now, how important is the mean free path? The mean free path depends actually strongly on the atomic number of the scattering atom, atomic number of scattering atom. For example, if there is an 100 kV of electrons which are accelerated with 100 kV potential, then the mean free path, remember the mean free path is the distance at which the electron can scatter. So, for the gold sample you can see that the mean free path is very less, means the scattering tendency will be it shows that the scattering tendency is very high. For the carbon the mean free path is very high, okay. And this elastic scattering of the electrons, the main contribution is for the diffraction patterns, okay, which are very important in TEM. Okay, this will come later in the class. And the strength of scattering depends on the atomic number, as I told before, and this is described by the atomic scattering factor, which is F. So, the amplitude of scattering from the atom divided by from the single atom. So, this is the definition of atomic scattering factor, which is the amplitude of scattering from an atom divided by the atom from a single electron. Okay. So, now you hope that we understand what is the elastic scattering. So, remember, elastic scattering contributes to the diffraction patterns, and it is the probability of elastic scattering is inversely related to the energy of the primary electron and also the angle of scattering. Now, we will come to the inelastic scattering. Fine. Inelastic scattering, what does it mean? If there is a detectable change in the energy of the primary electron beam, it means that whatever the energy the primary electron has, the E0, when it interacts with the sample, then what will happen is it loses some of the energy, and depending upon the amount of loss of this energy, different types of scattering can be divided, or different types of radiations can be produced. Okay. Usually if the energy is lost greater than 0.1 electron volt, then we call it as a inelastic scattering. Okay. So, this is due to the interaction process. So, here what we tell is energy lost by the primary electron and transferred to the electrons or atoms of the specimen. So, whatever the energy is lost, usually that lost energy is actually transferred to the electrons and the atoms of the specimen, due to which there will be a release of certain radiations and different types of energies. And this inelastic scattering is also responsible for stopping of an electron by a solid. Okay. So, when the electron goes into the sample, because it interacts, there is an inelastic scattering, means it loses the energy, but at a certain point it will be stopped by in the solid. Okay. So, here almost all the kinetic energy carried by the primary electron will end up as heat in the specimen, and this production of heat will release certain amount of energies that we will discuss now, and small proportion of the energy escapes as X-rays, which is used for the spectroscopy, light or secondary electrons used for imaging and analysis. Fine. So, these are the result of inelastic scattering, which is the result of loss of certain energy of the primary beam to the specimen or to the electrons or atoms of the specimen. Now, based on the amount of energy which is absorbed by the specimen or which is lost from the primary beam, you will have a different types of energies which can be released. These energies are either phonon scattering, plasmon scattering, single valence electron excitation, inner cell excitation, and inelastic scattering and absorption. Okay. So, this order goes with the energy loss. It means that very less amount of energy loss, it can lead to phonon scattering or the plasmon scattering. For the higher energy loss, you will have a single valence electron excitation and inner cell excitation, and here there is a complete absorption. Fine. So, first we will cover about the phonon scattering. What is phonon scattering? Usually when an electron interacts with the sample, it will develop the atomic vibrations in the solid. Okay. So, phonon scattering, it is a result of there is a the level of loss is less than 1 electron volt. Okay. Remember the in TM and SEM we are dealing with 30 kilo electron volt, or in TM we are dealing with up to 300 kilo electron volt, 300 kV. So, you can see the figure here. If there is a less than 1 electron volt is lost, that corresponds to the atomic vibrations which is related to the phonon scattering, and the whatever the loss energy, that one less than 1 electron volt, it contributes to the heat or the atomic vibrations in the solid. So, a primary electron loses energy less than 1 electron volt by exciting a phonon, that effectively heating the solid. The mean free path for the high energy electron is very large and few microns in this case. Okay. So, all the electrons which remain in the solid are likely to excite phonons after they lost larger amounts of energy, and this is how the solid is heated by the electron beam. So, whatever the radiation coming after heating of the sample, these we called as a phonon scattering. The scattered electron is deflected by large angles, it is more than 10 degrees, okay, and it can be used for the image contrast. Usually the phonon scattering is very important for heat transfer, then spin relaxation, thermal expansion. Okay. So, the phonon scattering we can term it as the quanta of elastic waves which are generated during and which results in the atomic vibration in the solid, and usually and effectively heating the solid. Okay. Now, the next is the plasmon scattering. Okay. So, if your energy, if your beam, so remember the beam energy, if you are talking about the transmission electron microscope, it is 30 kilo electron volt, 300 kilo electron volt, sorry. For SEM it is 30 kilo electron volt, for TEM it is 300 kilo electron volt. Now, if the primary electron beam loses energy between 5 to 30 electron volt, then it excites a plasmon. Okay. So, what is a plasmon? It is defined as it is a wave in the sea of electrons in the conduction band of a metal. Okay. So, it is what we call it is a waves in a sea of electrons. Okay. So, here the mean free path, the lambda is very short and it is only few hundred nanometers. This frequent occurrence in all electron solid interactions, and usually it is dominated by the energy loss spectrum. Energy loss spectrum, there is another method which in the TM what we use is yields, electron energy loss spectrum. Okay. So, with this we are using, so we can actually based on the energy loss we can identify the chemical species or the composition of that particular sample, correct. So, this is dominate the energy loss spectrum, which is called a plasmon scattering, and it is nothing but the waves in the sea of electrons. Okay. Usually the plasmon scattering is to study the surface plasmons in microscope using yields, and this also a large application in nano antennas, then sensors, optical detectors, etc. Fine. So, this is a plasmon scattering. Now, we will see that first we discussed about the phonon scattering, which is a less than 1 electron volt. Now, we talked about this is phonon. Now, we talked about the plasmon, which is 5 to 30 electron volt of loss of energy. Now, the next is the single valence electron excitation. Okay. And usually the primary beam, here what will happen is that the primary beam which has an energy of E0, it transfers energy to the single valence electron. It transfers energy to the single valence electron. What are the valence electron? You can see that if any orbital is there, if any atom is there, the outermost shell, the valence shell, whatever the electron, these are called valence electrons, and these valence electrons get the energy from the primary beam. So, the primary electron transfers some energy to a single valence electron rather than sea of electrons. Here the mean free path is very large, it is a few micrometers, scattering angle is also very small, and this is not much useful in the electron microscopy. Fine, this is a type of single valence electron excitation. Now, next comes the inner shell excitation. So, if you see an atom, it has a nucleus, it has a certain shells. Okay. You will have a K shell, L shell, M shell, K, L, M shell, okay. And depending upon, and these shells contains the electrons are or present in these shells, and they have a definite energy. So, these all shells have a definite energy. So, this but inner shell excitation means the primary electron beam will travel and it will knock out the inner shell electron out, either K or either L shell. This is L shell, this is K shell. But you can see that the K shell is much closer to the nucleus. So, what will happen? Your binding energy with the nucleus of that K electron is much higher than the L electrons. So, the binding energies are very high for K and L shells. The energy lost by the primary electron is very high. So, it will be few more than few hundred electron volts. For example, for a carbon K electron, you will have to 283 electron volt to remove a carbon K electron. But if it is a tungsten K electron, then you need a very high energy loss, which is around 69508 electron volts to knock out the K electrons. In this case, the mean free path is very large, few micrometers, and in this case the inner shell excitation, the secondary effects are very useful. Okay. Remember, these are inelastically scattered. So, whatever the energy loss is there, that is absorbed by this particular electron which is present at a particular shell, depending upon the which shell it is, and with taking up those energy, these electrons can be knocked out. Okay. So, the cross section for this inner shell excitation drops as the primary electron energy increases. Okay. So, typically this is given by sigma equal to 1 by EC into E0. E0 is the primary beam energy, correct, and the critical energy to excite an X-ray increases with the Z, because with increasing its Z, the number of electrons and number of protons also increases. So, your binding energy also increases with the increase in the Z. So, these are called inner shell electron. Now comes to the inelastic scattering and absorption. What is this? So, here in solids, whatever the primary electron interacts with the sample, the many scattering events will occur until the electron is stopped or leaves by the surface. Okay. Stopped means it is completely absorbed onto the sample. So, the trajectories of few electrons by simulating with the Monte Carlo methods, which introduces many angle of scattering probabilities, correct. So, majority are brought to halt within the solid, but few are back scattered and leave the specimen. Okay. So, the volume with 95% of primary electrons are brought to rest, it means they are getting absorbed into the sample, and it is referred to as the interaction volume. So, you can see that this is the Monte Carlo simulation of an aluminum with a interaction of the electron beam, and you can see that the electron travels, scatters, loses energy and travels, and it stops at a certain position. So, each electron will stop at a certain position, and this joining these points of this distance where these are stopped, it corresponds to your interaction volume. So, for thin specimens, the absorbed means not detected in the experiment, and these scattered through an angle greater than theta. Okay. So, here there is an equation which is called the Lambert-Beer law, okay, where I upon I0 is the fractional intensity which is remains after absorption in a thickness x, and n is the number of scattering atoms per unit volume. Okay. And this n can be given by Na rho by A, where Na is the Avogadro number, rho is the density, and A is the atomic mass. Okay. So, this way we can estimate the fractional intensity which remains after the absorption in a thickness x. Now, little bit we will talk about the secondary effects. As I told you, when an electron beam interacts with the sample, it loses energy, especially in knocking out of the electrons from the inner shell, it generates a secondary effects. First, we will describe the interaction of electron beam with the sample. Now, here can see that the secondary effects, most of the secondary effects can be written as either secondary electrons or the backscattered electrons. What are the secondary electrons? The secondary effects are caused by the primary beam which can be detected outside the specimen. Okay. So, when the electrons which hits to the sample, what will happen? It knocks out the valence electrons of the surface atoms. If they knocks out the valence electrons from the surface atoms, these electrons will escape from the specimen with energies below 50 electron volt. Remember, for SEM we are using 30 kilo electron volt. So, if these energies less than 50 electron of the valence electrons will escape, and the yield is high and abundant, and these are used for the imaging of the surface atoms, surface of the sample surface. Okay. Then there is another type of interaction which is a backscattered electrons. What are backscattered electrons? The primary electrons leaving surface before giving up all the energies. Okay. So, here the primary electron will go to the sample, go into the sample, and before leaving all the energies it gets backscattered again from the sample surface, and those primary electrons which are backscattered are again detected. So, it has a information related to the inside the sample backscattered, okay, and they are not as numerous as secondary electrons, but carry high energies. These particular BSC electrons are used for imaging and diffraction in SEM. Diffraction in SEM means it is used for the EBSD, electron backscattered diffraction. Okay. So, these are the primary secondary effects. Now, there are other secondary effects which are very important to understand, and these are caused when the primary beam which can be detected outside the specimen. Okay. So, the first type, there are 3 types of the interaction here, secondary effects. The first is relaxation of excited atoms. What does it mean? If an electron has been knocked out of an atom in the specimen, the atom is in the excited state, okay, but it is in the unstable state, it is in the excited state, or we can call it as a high energy state. Remember, the electron has been knocked out of the atom in the specimen. The empty electron state means the electron has been knocked out. So, the space, it has created a space. The empty electron state will be filled and the atom get relaxed, due to which it will give off the excess energy as secondary effect. Okay. Based on the which type of electron is getting knocked out, based on that different types of different excess energies can be released as a secondary effect. The first type is cathodoluminescence. What is cathodoluminescence? When the vacant electron state is an outer state, it means that if you have a valence shell, if the electron hits to the electron on the valence shell and this particular electron gets knocked out, if the vacant electron state is an outer state, then the energy to be given off will be very small, okay, and the electrons which are in the conduction band, usually those electrons will occupy these vacant sites of the valence. Okay. So, these conduction electrons, okay, those occupy the vacant sites of the valence electron, and these are commonly emitted in the form of a photon which may be in the visible range. So, these are called cathode luminescence, and cathode luminescence is used mainly to understand their uses are resonance effects, band gap defects, it is also used for the light transport, electronic structure, and especially used for this in semiconductors. Okay. Remember, cathode luminescence, it is the energy released when the electrons which are in the conduction band occupy the vacant electron state in the outer shell, which is knocked out by the electron beam. Okay. So, this is the one type of relaxation of excited atoms. Another type of excited atoms is when an electron knocks out the inner shell electrons. So, now you have a nucleus, you have a shells. If an electron comes and knocks out the inner shell electrons, this may release 2 types of energies. Okay. So, here the vacant electron state is an inner state, then the energy to be given off will be very large, because in the vacant states the energy, the electrons are bind towards the nucleus. Okay. So, they need higher energy to knock out. So, whenever there is an electron which knocks out from the inner shell, if the outer shell electrons will go and occupy these inner shell electrons, they will produce X-rays, and these X-rays are characteristic, and depending upon the energy, whether from the M shell to the K shell, whether L shell to the K shell, the X-rays have a different wavelengths, and these are characteristic of every element, and these X-rays are used to quantify for the composition analysis. Okay. So, what are the X-rays? Here a single outer electron jumps into the inner shell vacancy, which is created by knocking out of electron from the electron beam, and the energy is the difference between the energies of the two excited states. Okay. So, here the lambda is given by Hc by delta E. These are the generation of X-rays. Now, there are a second type of excited state when the inner shell electron knocks out is the Auger electrons. These are called Auger electrons. What are Auger electrons? These are alternate to X-rays. What happens is there, when an inner shell electron is knocked out from the atom, then what will happen? There will be a vacancy, there will be a first vacancy, correct. Then the outer electron that jumps into the vacancy and other outer electron that leaves carrying the energy. It means that when an electron knocks out from the inner shell, what will happen? The outer electron will jump into the inner shell electron, and the whatever energy is released during that time, that energy will be used by the other outer electron that leaves the carrying the energy, and these electrons, the outer electrons which leaves the carrying energy, these are called Auger electrons, and these usually used for the surface studies, sometimes chemical and composition analysis. Fine. Okay. So, with this we will end this class now. So, I have given you a brief interaction of the electron with the sample and what type of signals we produce, and depending upon the elastic and inelastic scattering, you can get different types of secondary effects. Elastic scattering, mostly these are this produces diffraction patterns which are very useful for crystallography information in TM, and inelastic scattering, based on the energy loss, different types of radiations are released and which can be used for specific purposes. Okay. So, with this I will end this class now, and we will meet in the next class. Thank you.